Okay, so one of the final video of 4.4, energy in reactions. In this video, I would like to go through this part really, explain the following relationships and undertake calculations involving their rearrangements. Now, I haven't got an example for rearrangement yet, but hope you get the picture. But you'll be practicing using some of these formula. I'm going to the second last slide in the lecture note. So this sample problem should let you use some of those, two at least, of those formulae. So the question is, 3 grams of octane was burnt in a calorimeter with excess oxygen. The 1000 ml of water in a calorimeter rose from 23 degrees Celsius to 57.6 degrees Celsius. Octane's molar mass is 114.224 grams per mole. So that's given too. Alright, so 3-part question. Firstly, calculate the heat released by the combustion reaction. 2. Determine the molar heat, or molar enthalpy that is, of reaction. Firstly, we'll try doing it via specific heat or enthalpy of reaction, and directly. Finally, write a thermochemical equation for this reaction. Remember, thermochemical equation requires you to have delta H value as well. So yeah, that's why you need to calculate molar enthalpy first. Alright, let's see how, not this one. Let's see how it work out. So question 1, what would you need to calculate? It's heat. When you hear the word heat, think of Q. So we'll start with Q. We'll start with Q. The equation goes heat capacity of water, that sometimes gets accompanied by P as well, Cp, but that really means the same. So Cp or just C, either way, it's the same. Now Q is heat. I might just calculate it in joules, because that's what's given in Cp. M is a mass, so it's in grams of water, by the way. Cp is joules per grams per degree Celsius. Remember, it's the amount of water that is there, but for you to change the temperature of it by 1 degree. And it shows how many joules it would require. And delta T, needless to say, hopefully, it's just degrees Celsius. So by cancelling these out, by multiplying them, you should just leave joules as the answer. So let's see. What was the mass of water used? According to the question, it's 1000 mils, which is interchangeable to grams. So that's 1000. Let's use multiplication sign. Cp, C, is 4.18. Yeah. And delta T, now you might have to find it by putting these numbers in. 57.6 take 23.0. Alright, so all the numbers are there. So if you type that into calculator, hopefully I did the right thing too. 144,628. I put a dot there because I already converted that into kilojoules. Otherwise, you will have 6-digit number, so 144,628 joules as your answer, which is still okay. But I think it will become nicer when you have that. Now, I'll talk about significant figures later. So I will leave it with this symbol here. I will let you think about significant figures here. Question 2, by the way, I might have to get rid of that. I'll have to get rid of this. So let's talk about significant figures. What do you think is the right significant figures you should be using? Well, according to the definition of it in chemistry, you have to pick the smallest significant figures that was used in the calculation. Okay? So in this case, what was used? A 4.18 that was given 1,000. That's only having one significant figures. No, in the question it says 1000.0. So that's 5 significant figures. So that's larger than 3 significant figures. So let's use 3 significant figures for this answer here. So 144, that's already 3. So the fourth figure needs to be rounded up or down. This 6 is more than 5, so it need to be carried up. 145 is the 3 significant figures here. Unit is in kilojoules. Now, if you're doing this in joules, you would have to do, now I'll write that later, 145, and then 0, 0, 0. First 3 figures are significant. Rest are not really significant enough for 3 significant figures to be considered. So these would be the right values for 3 significant figures. All right, moving on to question 2. Now, part 1 is saying, well, by a specific heat. That's the heat generated by this reaction. So let's make use of that. So Q2, 1. Okay. What you're trying to calculate is the molar heat. So you, in the end, want to find delta H. Okay. Now, one of the formulas which contain delta H was something looking like this. So delta H would be kilojoules per mole. That is, that needs to also be in kilojoules per mole if you want to find that. All right, now we found Q, didn't we? So let's use that. By the way, you can't use 145. That's already a rounded up value, so you want to keep original value for your second calculation. And for number of moles, you have to look at the question. 3 grams was used, and molar mass is given as 144, 2 to 4. If you put that in your calculator, you should be able to get 5506. Point. No. Yeah, no, that's correct. 6. That is in kilojoules per mole, but that is not in 3 significant figures. So all the numbers that we used, yep, in the question, it was given as 3.00. So that's actually the 3 significant figures there. Much larger than this, smaller than this one. That's 6 significant figures. So you would have to make that into. You can leave this though. 551 because that needs to be brought up there. but because there's decimal, you have to put 0 there. So for you to have the answer in 3 significant figures, 5510 is going to be the right answer. So 3 SF. Alright, hope that made sense, and you managed to use the other formula here. Now, there was another formula that you could use, even if you didn't find heat, the specific heat for this reaction before, you could still find it. Hope you remember the formula. That was delta H equals to MC delta T over 1000 N. Now, hope you all know these values here. Oops. Yeah, 1000 mils, 1000.0, that was given, wasn't it? Times by 4.18 times by 7, sorry. 0.6, take 28, 23.0 over 1000, number of mole would be this again, 3.00 over 144.224. Now, if you didn't make any mistake, you should be able to get same number here, and also same number after working out the significant figures. So I'm just going to use the same thing. Okay. Yeah. What this shows is that if you combine two formula to find out delta H, so if you knew Q first and then make the Q equals to delta H times by N equation and then reconfigure that, you get to find delta H. Or directly, by just knowing all the numbers and putting those into the formula. So either way, you should be able to find the same answer. Okay, let's do question 3. Question 3 is about thermochemical equation. Also, you remember what's required. Now, octane is the first thing you need to think about. What's the formula? C8H. If you remember homologous series, and also how to calculate the number of H. It's a alkane, so 8 times by 2 plus 2, that should give you this formula. Okay. Plus, you're burning this, so O2 is required. When it's burnt, it will become CO2 plus H2O. Now, thermochemical equation requires delta H to be part of that. So yeah, make sure you have that there as well. Now, things that you need to be careful of when you're balancing thermochemical equation is that delta H is in kilojoules per mole. What I'm saying is this octane here needs to stay as 1 mole. Because the balanced equation here will show how much energy will come out if 1 mole of octane was burned. Okay? So, if you could do all the balancing correctly, you would normally go 2 lots of that and 16 of this, as well as 18 of this. But because you want to keep this as 1, at the end you should get 8 9 here. And this one would be not 25, but half of 25. So 12.5 oxygen atoms would be required to balance that. And thermochemical equation is the only place where you can do this. Okay? Now, delta H, that was calculated before, 5510. Now, please remember to add a negative sign in this case, because octane is being burned, meaning it's releasing energy. Delta H, but negative value is release of energy. 5510. Unit is in kilojoules per mole of it. That will be 3 marks out of 4 because we are still missing states. Liquid, gas, H2O could be gas, but I'll leave it as liquid. And that's everything you need for writing some chemical equations. The trick is to keep whatever that you are burning in combustion as 1 mole, because that corresponds to that number. If there were 2 moles, the unit won't be kilojoules per mole, would it? So that's the end.